Today we're going to cover Chapter 10, Section 6. We're going to cover segment relationships in circles. So the first one, we need to first define what a segment of a chord is. So when two chords intersect in the interior of a circle, each chord is divided into two segments called segments of the chord. So for example, if I take this chord AB, notice when it intersects the other chord, it splits it up into a little piece here. So this is a segment, and so is this, EB. Then the other chord, the DC, that one would get split into segment DE here, and then segment EC. So this is what it means to have a segment of a chord. It just splits it into two smaller pieces when it intersects a second chord. The next slide has the theorem for the segments of the chords, and this is going to tell us how to find the measure of it. So Theorem 1018 is called the segments of a chord theorem, and what this one states is that if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Now, this theorem is not telling us that the segments are congruent. It's telling us that their products are congruent. So what it's stating here is that this segment EA, which is right here, times this segment EB is equal to segment EC, which is here, times ED, which is here. So it's telling us their products are congruent, not that the chords are congruent. The next is a definition, and this is the definition of a secant segment. Generally, a secant is a line, but in this case, it's going to be a segment, and a secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. The part of a secant segment that is outside the circle is called the external segment. So in this picture here, this whole piece is the secant segment. But the darker red here, this is the part that's outside of the circle. So this is called an external segment. Then the blue line, and the definition is going to come on the next slide. This is a tangent segment. Notice the tangent is only hitting the circle at one point, where the secant is actually passing through the side of the circle. So it's going through it, and then it's stopping at the endpoint on the side of the circle. Pretty good? Okay. So this is the definition of a tangent segment. A tangent segment is a segment that is tangent to a circle at an endpoint. So the examples here in this picture, the blue line, this is the tangent segment. Again, notice it's hitting the circle at only one point. So PS is a tangent segment. PR is a secant segment, this whole thing here. And the piece of it that is outside of the circle, PQ, is the external segment. So it's outside of the circle. It's a piece of the entire segment PR, but it's the segment that's outside. Mm-hmm. Pretty good here? All right. let's do a theorem. So the next one is Theorem 1019, and this one is called Segments of Secants theorem. So notice both of the lines in the figure, Ln and Pn, these are both secant lines or secant segments. So if two secant segments share the same endpoint, and that endpoint is n, outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external. So it's whole times external, whole times external. So here, our first secant here, Ln, this is the whole thing. And then the external piece of that secant is Mn. Then over here, we have Pn as the whole, and then the external piece of Pn is On. So you're going to multiply the whole thing times its external piece. So remember, the whole thing is the Pn, and then the little piece that's outside of the circle is the external piece. So this is when you have two secant segments. The next theorem is for a secant and a tangent. So ML here, this is the tangent line, and JL, this is the secant segment. And this is the whole thing, JL. JL is the whole, and KL is going to be the external segment. So this one states if a secant segment and a tangent segment share an endpoint, and again that shared endpoint is L, then the product of the lengths of the secant segment and its external segment equals the square of the lengths of the tangent segment. So it's the tangent squared is equal to whole times external. Now we're going to do examples of all of these theorems and definitions we just learned. Let's take a look at example A1. Notice these are two chords that are intersecting inside a circle. So remember, the product of those segments are going to be congruent. So these are two chords. And when two chords intersect, the product of their segments are congruent. So for example, I have this segment here, or this chord here, which is split into this segment, which is make it up of 12, and then I have 2. So for this one, I'm going to do 2 times 12 is equal to the other chord's segments. So 3 is the segment here, and so is x. So I'll do 3 times x. I'm going to multiply the 2 and the 12. Set that equal to 3x, divide by 3, and x equals 8. So if all they're asking us to do is find x, that's all we need to do. Let's say it said to go back and find the lengths of the segments. So let's say I add in some variables here. Let's say I say that this is A, B, and this is CD. So let's say they say find the length of AB. All you have to do is 12 plus 2, and the length of AB is 14. Let's say they said also to find CD. CD, we just found x to be 8. So if I do 8 plus 3, you can see that that's going to be 11. Notice the two chord lengths are not congruent, but what's congruent is their products. So just be careful there. Let's go ahead and go to example B. Okay, so this second picture, this is a picture of a tangent and a secant segment. So the formula we're going to use is tangent squared is equal to whole secant times the external piece. So again, from my picture, my tangent is x, so I'm going to square it, x squared. My whole secant, I can find that by adding 18 plus 6, and I get 24. And then the external piece is the 6. I'm going to multiply 24 times 6. I get 144. And then to solve for just x, I square root both sides. I get plus and minus both 12. But in this particular problem, I do not want to keep the negative answer because I can't have a negative tangent. So the only answer here is positive 12. Let's try the next example. This is an example. In this picture, these are two secant segments. So the formula that I'm going to use for both is going to be whole times external is equal to whole times external. So whole times external equals whole times external. So for my first secant, it's up here. I can easily find the whole length of this by adding 8 plus 4. And the whole length of this secant segment is 12. My external piece is the 4. And then my next secant segment is over here. And I can find its whole length by adding x plus 6. And I'm going to leave it like that. And then I'm going to multiply it by its external piece, which is the 6. I need to multiply and distribute. So 12 times 4 is 48. I'm going to distribute the 6 to the x and to the 6. And now I can solve for x by subtracting 36. And get 12 is equal to 6x. Divide by 6. And x equals 2. Example D. This one is a tangent and a secant. So we already did this one, but we'll do it again. So 10 is the tangent, and the 2x plus x, this is going to be my secant segment. So the whole length is 2x plus x, which is 3x. And then the external is just the x. So the formula I'm using is tangent squared is equal to whole times external. So my tangent is 10. So 10 squared. And then the whole, which is the 3x, and then times the external, which is x. So 3x times x. I'm going to square the 10. I'm going to multiply the 3x and the x. And now I need to solve for x. I need to isolate, so I'm going to divide by 3. And I get 100 over 3 equals x squared. I don't want x squared, I want x, so I have to square root both sides. And this gives me x is equal to plus and minus the square root of 100 over 3. Now, if the instructions say to leave it in simplest radical form, we need to simplify this. Now, if it just says, give your answer rounded to the tenths place, then I would find the square root of 100 divided by 3. And that is going to be 5.77 rounded to the tenths place, 5.8. But you'll probably have to leave it in simplest radical form. So now what we need to do is simplify this 100, and I'm going to break it apart. The 100 is a perfect square. It'll come out as a 10. The 3 is not perfect. It'll stay underneath the radical. But remember, you can never ever leave a square root in the bottom of a fraction. So we need to rationalize. So we get plus and minus 10 square root 3 over 3. Again, I will not keep the negative because I don't want a negative secant. So the only answer here would either be the 5.8 or 10 square root 3 over 3. So you would have to read the instructions. If it says to leave it in simplest radical form, then it's the 10 square root 3 over 3. If it says to round to a specific place, like the tenths place, then the answer would be 5.8. Now, generally, like I said last week, generally this circle chapter involves a lot of factoring. For the homework tonight, we have modified the questions so that you do not have to factor. There's one I believe you have to factor, and it's a simple factoring question. So what I want to do is I'm going to add one more example to this where you're going to need to factor to solve. So if you want to add a page to your notes, I'm going to add one example. I'm going to draw my circle. I'm going to draw in two secants. So these are my two secants meeting at this external point. The piece of this segment is 2. This is x. This is 4. This is 8. So when you have two secants, remember the formula is whole times external equals whole times external. So for this secant here, to get the whole, I'm going to do 8 plus 4, and it's 12. The external piece is the 4. So 12 times 4. And then for this secant down here, I can add 2 plus x. That's going to be the whole amount. And then x is the external. So 2 plus x times x. We need to multiply and distribute here. So 12 times 4 is 48. 2 times x is 2x, and x times x is x squared. Now, I need to get this into a trinomial that I can factor. So what I'm going to do is I'm going to subtract 48. And then I'm going to rewrite the trinomial in standard form. Standard form means you put the x squared first, then the x term, and then the constant. When you factor a trinomial, something simple like this, you're going to look at this last term. You need to find the factors of negative 48 that when you add those two factors, you'll get a 2. So I'm looking for two numbers that when I multiply them, I get negative 48. But when I add the same two numbers, I get a positive 2. So what I start by doing is I start listing my factors of 48. So 1 times 48, 2 times 24, 3 times 16, 4 times 12, 5 doesn't work, 6 works, and then 7 doesn't. Now notice the numbers I was looking for to multiply together needed to make a negative 48. The clue here, and this is all Algebra 1 skills that you should remember how to do, the sign of the middle term is positive. That sign goes on my bigger factor. So my smaller factor here is going to be the negative. So now I need to figure out which one of these combinations, because these are all ways that I would multiply to get negative 48. Now I have to go back now and figure out, change these signs now, and which of them, when I add them together, give me positive 2. And you can see the very last one is the one, negative 6 plus 8 gives me positive 2. So now I write my answer as two binomials. The factors of x squared go here, and the factors of the negative 48 go here. It doesn't matter if you write x plus 8 first or x minus 6 first. They both FOIL and give us the same answer. Now, we're not done here because we needed to find the value of x. So what we need to do is take each of the factors, set them equal to 0, and solve for x. X equals negative 8. X equals 6. Again, you're going to go back up there, see if it makes any of the secants negative. The negative 8 will when I plug it in here, because 2 plus negative 8 gives me negative 6. So this answer gets thrown away, and my only answer here is the x equals 6. So just a little bit of a review for factoring a simple trinomial where there's no leading coefficient in front of x squared. It's just a 1. So generally this chapter, this homework, was full of factoring. Again, we modified all of the questions except for one. We left one simple factoring question. Now, let me show you the answers to the homework since we switched the variables. Yes?
Is it always going to be the positive?
It all depends. You have to plug it in because sometimes the negative will work. So notice when I plugged it in up here, if I were to put a negative 8 here, 2 plus negative 8 gives me negative 6. I don't want a negative secant here, so that's why I threw that one away.
So the negative 1 may work, but only if that other measurement is bigger.
Correct.
Okay.
Yep.
Thank you.
You're welcome. All right, so let's take a look at the 10.6 homework. I'm going to give you the answers if you want to write them down for those of you who want to check your answers tonight, because I did change them.